All right, so you're here because you really want to get right into the thick of things, right? And when it comes to medical imaging analysis, well, there's always a lot going on.
Yeah.
But
Lots
today,
to keep up with.
today we're going to try and give you that shortcut to
Absolutely.
understanding
Yeah.
a really big development.
Yeah, consider this your direct route
And how we're analyzing images in the medical field.
to understanding.
So think of this as us doing the hard work, sifting through the complex research
The essential.
so that you don't have
something
Okay.
that could be a real game changer.
So we're diving into
Medical imaging. Yeah.
MedSAM2. No,
Nice.
this isn't just another AI tool that's just popped up, in this constantly evolving world of technology.
Exactly.
This is something called a foundation model,
Okay.
and it's specifically designed for understanding and outlining or segmenting
Foundation model. That's key.
3D medical images and video.
To understanding its potential.
And that concept of foundation model is really what's going to unlock
It is.
its potential.
You see, older AI tools were often designed for very, very specific tasks.
Right.
Maybe picking at a certain type of tumor in a particular type of scan.
Right. Very narrow.
MedSAM2 is different.
Okay.
Much more general.
All right.
It's learned from this absolutely massive and incredibly diverse collection of medical images and videos.
So almost like instead of having all these different AIs for all these different problems, we might be able to have just one
That's the idea.
that can understand everything from, a CT scan of the abdomen to an ultrasound of a moving joint.
It's a more adaptable, versatile approach.
Yeah, it's a really cool idea.
Yeah.
So the source material for today's deep dive is a research paper.
All right.
And it's titled MedSAM2. Segment anything in 3D medical images and videos. And we've gone through all the details. We've pulled out what we think are the essential insights.
Yeah.
And now we're going to try and
Bring them
to you.
straight to you.
Okay.
Yeah.
So our mission today is pretty straightforward.
Okay.
We really want to break down MedSAM2.
Yeah.
We want you to understand what it is.
At its core.
At its core, how it does what it does.
How it works.
Without getting too bogged down.
Without getting bogged down.
In the technical jargon.
In the technical details.
And what makes it special
Yeah.
compared to what came before it.
What makes it unique.
And why is all of this significant?
And why it matters.
For making medical image analysis faster?
Yeah.
More accurate?
For efficiency and accuracy.
More efficient.
Exactly.
Okay, so where should we begin our exploration?
Well, I think a logical starting point is to sort of understand where MedSAM2 comes from.
Okay.
It wasn't built in isolation.
Okay.
It builds on a previous model called SAM2, which stood for Segment Anything Model 2.
Okay. And SAM2 was pretty impressive in its own right.
Right.
It could segment pretty much.
It was, yeah.
Anything.
It was quite impressive.
In everyday images and videos.
And a range of kind of general image and video segmentation tasks, yeah.
From, animals to objects, all kinds of things.
It showed a real ability to generalize across a lot of different situations.
Right, so it had a good general understanding.
It did.
But the researchers realized...
However, when they tried to apply it directly...
Applying that directly to medical images...
To a specific domain...
Was a bit of a challenge.
Of medical images.
Yeah, it's a different world, right?
It is, yeah.
A photo of a landscape is very different.
It is.
Than, like, a 3D MRI scan of the inside of the body.
Different types of visual information, different structures, different textures.
So how did they bridge that gap?
Yeah, they called it the domain gap.
Right.
So the central idea was to take that already powerful SAM2 model and then fine-tune it.
Okay.
For medical images, for the characteristics of medical imagery.
When they say fine-tune, what does that actually mean?
Think of it like you have a really skilled musician, Megan. They've mastered many instruments.
Okay.
And then they decide to specialize in one particular one.
Okay.
And the way they do that...
So it's still the same model.
It is, yeah.
But they're just refining it.
They're refining it, they're honing its skills, they're giving it specialized training.
And they do that by...
By feeding it a huge amount of medical images.
Right.
And the expert outlines of the structures within those images.
And they said enormous.
They did, yeah.
And I think the numbers were something like 455,000 3D image mask pairs.
455,000, yeah.
From CT, PET, and MRI scans.
That's right.
And then another 76,000 annotated video frames from ultrasounds and endoscopies.
It's a massive data set.
That's huge.
It is.
So it's really learning from a ton of examples.
Absolutely, and that's what really enables it to sort of go beyond.
Yeah.
just being good at one specific task, that scale.
And also the variety within that data, right? Not just the quantity,
Yeah.
but also the fact that it's seeing all different kinds of...
Yeah, a wide range of different organs, different types of diseases, different medical imaging techniques.
Okay, so MedSAM2 essentially learned the language of medical imagery by seeing a vast library.
Exactly.
Now, how does it actually perform the segmentation?
Well, MedSAM2 has a few key parts that work together.
Yeah.
First, there's the image encoder.
Okay.
Now, its job is to take each 2D slice from a 3D scan,
Right.
or each individual frame from a video,
Okay.
and extract meaningful information from it.
Okay.
They use something called a hierarchical vision transformer,
Right.
or HIERA,
HIERA.
which is just a more efficient and insightful way for the AI to sort of see and understand
the element.
the different elements within each image slice. Yeah.
Okay, so that's sort of the initial visual processing.
Yeah, like a more sort of detailed visual processing system.
Okay, what happens after that?
Next is the memory attention module.
Right.
And this is particularly interesting.
Okay.
Especially for handling 3D images and videos.
Okay.
Imagine it like a memory bank.
Right.
Where the model can keep track of what it has observed in previous slices or frames.
So it's not just looking at each individual slice in isolation?
Precisely.
It's remembering what it saw before.
It's using that information to maintain consistency in its segmentation.
Right, so it's understanding the bigger picture of the 3D volume.
Across the entire 3D volume or the video, yeah.
Okay, so that's pretty advanced.
It is. It's really interesting.
What's next?
Next is the prompt encoder.
Okay.
And this is how a user, typically a medical professional, guides the segmentation process.
Guides it.
Yeah, so in this case, they use bounding boxes.
Okay, so bounding boxes are basically just...
It's just a rectangle.
You draw a rectangle.
Around the area of interest.
Okay.
And that tells MedSAM2
what to focus on.
What to pay attention to.
And they decided to use bounding boxes because...
Well, because they tend to be less ambiguous than just clicking on a point, for instance.
Right, and so for the 3D images, how does that work?
So you draw the box on a central slice where you can see the structure clearly. And then MedSAM2 uses that to propagate or extend the segmentation outwards in both directions.
So it uses that as like a starting point.
Exactly.
Okay, so we've got the image encoder to see, we've got the memory to remember.
Yep.
We've got the prompt to guide.
To provide guidance, yeah.
What's the final stage?
The final stage is the mask decoder.
All right.
And this is where it all comes together.
Okay.
It takes the visual features from the image encoder, the contextual information from the memory, and the guidance from the prompt. And it combines it all to generate the segmentation mask.
So that's the final output.
That's the final output.
The actual outline.
The actual outline, yeah.
Okay.
And they did something called full model fine-tuning.
What does that mean?
It means they didn't just adjust a small part of the original SAM model. They allowed all the different components to be adjusted and learn from that medical data set.
And that leads to better performance.
Yeah, it's been shown to lead to better performance and a more nuanced understanding of the domain.
All right, so we understand how it works.
Yep.
Now, how effective is it?
Okay, well...
Let's talk about the 3D images first.
Let's talk about the 3D images.
How did it do?
So they tested it on a holdout 3D test set. Which had 40 different segmentation tasks. Across CT, MRI, and PT scans.
All right, and so they were looking at both organs and lesions.
Both organs and lesions, yeah.
Okay.
And they compared MedSAM2 against the original SAM models. And another leading model called Efficient MedSAM Top 1. And what they found was quite interesting. Just scaling up the size of the original SAM model.
So just making the original model bigger.
Yeah, just making it bigger. Didn't actually lead to much better performance.
Okay, so you'd think that just having a bigger model automatically makes it better.
Yeah.
But that wasn't necessarily the case.
Not in this case, no.
Interesting.
Yeah, it suggests that maybe that pre-training on everyday images wasn't quite enough
more complexities.
The knowledge it needs.
Of medical images.
For medical images, yeah.
Okay, and so...
Now, Efficient MedSAM...
Did that do better?
It did better than the original SAM models. In some areas.
But MedSAM2 was...
But MedSAM2 consistently outperformed all of them.
Okay, so it was the best.
It was the best, yeah.
And it achieved the highest DSC scores?
It did.
Across all the categories?
Across all the categories. CT organs, CT lesions, MRI organs, MRI lesions, PET lesions.
Yeah. So what were some of those scores?
Well, for CT organs, for example,
Yeah.
it reached a median DSC of 88.84%.
Wow, that's high.
With a range from 80 to 94%.
Okay, so very accurate.
Very accurate, yeah.
And were there any specific examples where it was particularly impressive?
Yeah, so for simple structures like kidneys and lungs, most of the models did okay.
Right.
But where MedSAM2 really shined was with more challenging targets, things like kidney lesions and the pancreas.
Things that have more
variable appearances.
Variation, yeah.
Yeah.
Okay, and I think you mentioned that the memory design
Yeah.
helped it achieve those more accurate boundaries.
It did.
So the fact that it can remember what it's seen in previous slices
That's right, yeah.
helps it to create
A more consistent and accurate boundary.
Yeah. Okay, so MedSAM2 is looking good for 3D images.
It is.
But what about videos?
Yeah, that's a whole other challenge.
Yeah, because videos have movement.
Movement, yeah.
Things are changing.
Yeah, the imaging device might be moving, the internal structures are moving.
Right.
So it's much harder.
And they tested it on
They did.
2 datasets, right? The CAMUS dataset.
Which is cardiac ultrasound.
So ultrasounds of the heart.
Of the heart, yeah.
Okay.
And this SUN dataset.
And SUN is?
Endoscopy.
Endoscopy.
Okay, so looking for polyps.
Looking for polyps, yeah.
Okay, so how did it do with the beating heart and those polyps?
So for the echocardiography data, MedSAM2 again showed really good performance in segmenting those key structures, like the left ventricle epicardium, and the left atrium.
So those are all parts of the heart?
Parts of the heart, yeah. And it showed higher DSC scores.
Okay.
And also more consistent results.
Right.
So it was more robust at tracking these structures as they move throughout the video.
Yeah, that makes sense, because with a beating heart, things are constantly moving.
They are.
So it needs to be able to follow that.
Exactly.
Okay. And then with the polyps.
Oh, the polyps.
I remember they categorized the test set.
They did, into easy polyps and hard polyps.
Yeah.
What made the hard polyps hard?
Well, things like variations in contrast.
Okay.
Complex transitions between different types of tissue.
Yeah.
And sometimes changes in lighting or texture in the video.
Right. So all those things make it harder to
see the polyps clearly and to outline it accurately.
Yeah.
So.
And how did it perform on the Ely ones?
On the easy polyps, all the SAM 2.1 models and MedSAM2 did pretty much the same.
Okay. So
no real difference.
They could all handle the easy one.
They could handle the easy ones.
But
on the hard polyps,
the hard ones,
MedSAM2 was significantly better than all the SAM 2.1 versions.
And that makes sense, right? Because it's got that memory.
It does, yeah.
It's able to sort of
maintain that spatial understanding.
Right.
And avoid those over-segmentations.
Okay, so across both static images and videos,
yes,
MedSAM2 seems to be
a real step forward.
A big step forward.
Yeah.
Now, the paper also talks about another interesting thing, the human-in-the-loop innovation.
Yes.
So this isn't just about
right.
how well it can perform segmentation itself.
No.
But how it can actually be used to create the data sets that we need
to train AI models.
To train these models.
Yeah, it's about building those data sets.
And that's a major bottleneck, right?
It is, yeah.
Creating these labeled data sets.
Yeah, it's really time-consuming.
It's a huge amount of work.
Yeah, it's very expensive. You need specialized expertise.
Right. So the researchers came up with this idea of using MedSAM2 to help with that annotation process.
To speed it up, to make it more efficient.
And so instead of having a human expert go through and meticulously outline every
slice, every frame,
they've got MedSAM2 to assist them.
I'm saying, yeah.
So how does that work in practice?
So let's take the example of CT and MRI lesions.
Okay.
So the annotator starts by drawing a simple bounding box around the lesion on a central slice.
So the slice where it's most visible.
Where it's usually largest, yeah.
Okay.
And then MedSAM2 uses that to generate an initial segmentation mask.
Right.
And the human expert can then review that mask.
Make corrections.
Make any corrections. And they also specify the top and bottom slices.
Okay.
Where the lesion appears.
Gotcha.
And then MedSAM2 can propagate that refined mask throughout the entire volume.
So it takes what the human has given it and it extends it.
It extends it through the volume.
Okay.
And then the human expert can do a final review and make any final adjustments.
So it's a real collaboration between the AI and the human.
Exactly.
And the cool thing is, once they've annotated those cases,
they then use that data to further refine MedSAM2.
Oh, okay.
So the model's getting better.
It's getting better and better.
Yeah.
Each time.
With each round of annotation.
That's a cool idea.
It is, yeah.
So how much time did this actually save?
So for CT lesions, the initial manual process was taking around 526 seconds per lesion.
Okay.
And after 3 rounds of this pipeline, the average annotation time went down to just 74 seconds.
Wow, that's like an 85% reduction.
It is. It's a huge time saving.
And I think they were able to annotate more lesions.
They were, yeah.
In each round.
Yeah, they were able to annotate more lesions in each round because it was faster.
Yeah, so it's speeding up the whole process.
Exactly.
What about MRI liver lesions?
Very similar outcome.
Okay.
Manually annotating those lesions was taking about 520 seconds. And with MedSAM2, they got that down to 65 seconds.
So again, about an 85% reduction.
So 8% reduction, yeah.
So almost 4,000 liver lesions annotated.
In a fraction of the time.
Yeah.
It were taken to do it manually.
It's really impressive.
It is.
And it's not just limited to 3D images, right?
You know, they adapted the pipeline for videos too.
Yeah, and for the videos, they had the annotator provide prompts on the first frame.
On the first frame.
And then MedSAM2 would propagate that.
Through the video.
Human annotators would then refine it.
On keyframes, yeah.
And then MedSAM2 would update the propagation.
Yeah.
And then final adjustments made by a human.
Exactly.
And the time saving there was even bigger.
It was even bigger, yeah.
Yeah.
Manual annotation was taking about 102 seconds per frame.
Wow, that's a lot.
It is.
And they got it down to
8.4 seconds.
8.4 seconds.
Per frame.
Wow.
It's a 92% reduction.
That's a huge amount of time saved.
It is.
And it really shows the power.
It does.
This approach.
Of this human-in-the-loop approach.
So it's not just better at segmentation, it's also changing.
It's fundamentally changing.
How we create the
datasets
that we need for future AI models.
Okay, so we've got this great performance.
We've got this amazing ability to speed up dataset creation.
Yes.
Is this something that's actually accessible to people in the field?
That was really important to the researchers.
Okay.
They wanted to make sure this was a practical tool.
Okay.
So they integrated into a number of different platforms.
Okay, like what?
Well, 3D Slicer, for example.
Okay, and 3D Slicer is
It's a very widely used open source software for medical image analysis.
So people can just use it.
They can just use it within their existing workflows for things like segmenting lesions and organs.
Okay, what about for people who are more comfortable with code?
For those who are more comfortable with code, they have a command line interface.
Right.
And they've also integrated into things like Jupyter Lab and Google Colab.
So Colab is that cloud-based platform.
So you don't need
your own fancy hardware.
You don't need your own powerful hardware.
Okay, that's good.
And it's also available on Gradio.
Now what's Gradio?
It's a really simple web-based interface.
Okay.
So you can interact with the model.
Right.
Without any coding knowledge.
Okay, so that's really good for
interactions,
for quick interactions, for video annotation.
Especially for video annotation.
So you can just
upload your video.
Right in the browser.
Yeah.
Okay, so they've really made it accessible.
They have, yeah.
Now, no technology is perfect.
No.
So what are some of the limitations?
Well, one is its reliance on bounding boxes.
Okay.
As prompts.
And what's the problem with that?
Well, for very complex structures.
Yeah.
Like thin branching vessels.
Right.
A bounding box might not be enough.
Right. It's too simple.
It's too simple.
Yeah.
It doesn't capture
that complexity.
The 3D spatial information.
Right.
So they suggest that in the future, they might explore other types of prompts. Like
what?
Interactive points.
Okay.
Maybe text descriptions.
Or even like freehand drawing.
Or scribbles.
Yeah. Okay.
Another limitation is the fixed memory design.
Okay.
So it always uses the 8 most recent frames.
Okay.
Or slices.
And that's fine for a lot of cases.
It is, yeah.
But what if something moves quickly?
Well, if something moves very quickly or it disappears and reappears, it might lose track of it.
So they suggest maybe the more
adaptive memory.
Flexible memory.
Yeah.
And the final limitation
is the need for a GPU.
Right, so that's a pretty powerful...
Yeah, it's a powerful piece of hardware.
Yeah.
And that might limit its use.
In certain settings.
Yeah, in settings where you don't have access to the GPU.
So they're working on...
They're working on optimization techniques.
To try and make it work.
To make it run on CPUs.
On just regular computers.
Yeah.
Okay, so some limitations, but the researchers are aware of them.
They are.
And they're working on solutions.
They're working on solutions.
All right, so let's bring it all together. What are the key takeaways for our listener?
So I think the main takeaway is that MedSAM2 is a big step forward
Yeah.
in medical image and video segmentation.
And it
For accuracy.
improve accuracy, especially for those complex cases.
Especially for complex cases.
And for videos.
And videos, yeah.
And maybe even more importantly.
Even more transformative, perhaps.
It is its potential to change how we create.
To accelerate the creation of
large data sets.
Those large data sets, yeah.
Through that human-in-the-loop approach.
Yeah, that's a real game changer.
And it's not just theoretical.
No.
It's actually being integrated into
They're practical tools.
Real-world platforms.
Yeah, absolutely.
So it's something that people can actually use.
Yeah.
All right, so we've had a really interesting deep dive here.
Yeah.
Into MedSAM2.
We have.
And I want you, the listener,
yes,
to think about some of the broader implications of this technology.
Yeah.
What could this mean?
What could this mean?
For the future.
For the future of diagnostics.
Treatment planning. For research.
Large-scale medical research.
What new discoveries might be possible?
What breakthroughs?
When we can analyze these images and videos.
Faster. Accurately.
And build these large data sets.
More efficiently.
Much more efficiently. Yeah. It's really something to think about.
It is.
Thanks for joining us.
Thanks for joining us.
On this deep dive.
Into MedSAM2.
Into MedSAM2.